2x times, hey, what's another way you can rewrite cosine squared back from pre-cal? Actually, more complicated way. What was the Pythagorean identity? Sine squared x plus cosine squared x equals 1. So if I solve for cosine, I can rewrite the cosine squared x as 1 minus sine squared x, right? Now, the reason I'm doing that is because where I'm going with this has nothing but sines in it, right? So the only way I can get that cosine that was there to go away is to perhaps make it 1 minus sine squared x. And we still had dx. Do y'all see that? Now, this is multiplication, so this now has to pass through here and here, doesn't it? All right. Here it comes. It's about to happen. Okay, the original problem, right? Here was the original problem. Right? That was the original integral. We know right now that it is negative sine to the n minus 1 of x cosine x plus n minus 1 times the integral of this. So when you do this times 1, it's itself, right? So sine to the n minus 2 of x. And then when you do this times this, it's subtraction, right? Because you have positive times a negative. So it's minus, and what is sine to the n minus 2 of x times sine squared of x? Sine to the n, right? Same base, sine x, add the exponents, n minus 2, add 2, and minus 2 plus 2 is just n, isn't it? So this is minus sine to the n x. And then dx. I haven't taken an antiderivative yet. Y'all okay with this? This is about to be pretty awesome. Does anyone see it yet?
Yes. Oh, you can separate the integral, right?
We can split this into two integrals, can't we?
You can add that to the other side.
And then this is the one over there, isn't it? And I can bring it over to that side, like the rabbit out of the hat. So watch. Integral sine to the nx dx equals negative sine to the n minus 1x cosine x plus n minus 1 integral sine to the n minus 2x dx minus n minus 1 integral sine to the nx dx. So what I've done here is I've used the fact that if you have an integral of something minus something, right? You can split it into two integrals, right? And this number right here is being multiplied, so it has to distribute to both, so that plus n minus 1 has to go in front of both. But since this one was positive, I just left it here like this, positive. This positive thing times that negative, right, would become a minus? Yeah? This integral is the same as this integral. How many of them do I have to add to both sides to make it go away over here? N minus 1 of them. Right? This is a number. This might be minus 10, might be minus 5. So I need to add that number. That's how many of those integrals I have to add to both sides, right? So I need to add n plus 1 of these integrals to both sides. No, minus 1. Sorry, minus 1. That would have been a disaster. I'm adding this. All right, we good? Okay, this is gone. I erased the thing we're trying to get to. Oh, well. How many of these guys, are over here? N of them, right? Because how many of these are there right here? One of them. How many of these? N minus 1. What's n minus 1 plus 1? Just n? So we have n of the integrals that we are interested in is equal to negative sine to the n minus 1x. I heard, which makes, you had the little light bulb go off there? Yes? You see it? Plus n minus 1 integrals of sine to the n minus 2x dx. That's where we are now, because this was gone, right? And finally, divide by n. This is just a number, so just divide everything by n now. And when you do that, you get the reduction formula. Divide this by n, so I'll put negative 1 over n sine n minus 1x cosine x. Divide that by n, so n minus 1 over n integral sine n minus 2x dx. There it is. That's your reduction formula. Good? That's pretty cool, huh?
Is that formula on the one that you have on your, on the one that you're supposed to, on the formula sheet?
Like, is it up from your
It's not on those. These are the first, how many pages? 6. I think that's off page 8 or 9 on the formulas. No, and the reason is because I would never ask you to use this unless I gave it to you. But you need to know it exists. Okay, you need to know that there are formulas for things like this. And you need to know that these weren't like found in some cave by some alien being that came and gave us these formulas. Like, you know, we came up with these formulas on our own, right? All right, that's pretty awesome. I imagine that you could do the same thing for cosine. I imagine there's got to be a formula for cosine to the n then, right? And it probably works some formula. You could kind of get an idea of how they chose their u and their dv just by looking at it. All right, that's all I had for that. Now, so let me see here. I thought I'd bring up last semester's exam 1.
How many questions are your exam?
I haven't made the exam, so I can't tell you how many, but this is what they took last semester. This was their exam 1.
How many questions did you get last semester?
Let's see here. Hey, look at that. The bonus was to prove a reduction formula.
Did anyone do it?
Yes. 15 questions. So look, the first one, you know, has to do with inverse trig stuff. You know, just like evaluating. Like, find the value of this.
Oh, okay, use circle.
And then, you know, here's the derivatives. Take the derivatives. That's just making sure you understand derivatives of the different trig, inverse trig, hyperbolic trig. Prove an identity. I think that was a homework problem.
Yeah, it was.
It was.
Yeah.
I think this entire test was homework problems. Or similar to. Here's a second derivative with some initial conditions. Actually, this was the one where you have to go back all the way to the original function, then you get a system of equations. So remember I came into class a couple of days ago and someone asked about, I think it was, don't tell me her name, Kirsten, right? That it? Kirsten had said, yeah, that was the one I had trouble with because we hadn't done one like that in class, and then I did it. So that's what that is. Now look, I'm not telling you this is what your exam's going to be. I'm just giving you a flavor of what I've asked before, okay? Here's an acceleration function. Go backwards. Find the position function and find the position function at pi. So this problem is a little easier because you're given information about position and velocity. but it involves trig stuff, so that makes it a little harder. And then the integration begins. How would you do that integration? Right there. Split it up into 2, and it's just powers of x, right? You rewrite root x over x, and then you rewrite. That's just power rule. Got to split it up. This one? Basic u sub. What would u be? 4 plus x cubed. Because the derivative of it's sitting right there, almost. U sub, Alexis? What would u be? Square root of x. That's right. Because if you rewrote that integral, this is what the integral really looks like, right? And if you let u be root x, the derivative of it is 1 over 2 root x, and you almost have that. So you're just off by a constant. So that's basic u substitution. But if you start doing integration by parts on that, you're going to waste a lot of time. Which becomes one of the bigger issues on tests like this. Ooh, that's weird. Do you want to do that one? Yeah. That's why I was showing you this. There's a few on here I thought we would do if we had time. Was that a homework problem?
No, but it was like to more powers.
To the third, you
Yeah.
can split it up.
Yeah. That was the one that you were like.
This is an integration by parts? Or no? What would you choose for your u if you're going to do integration by parts here? What would you choose for u? X, because it gets better when you differentiate it. But that means that you're going to need to be able to integrate everything else. So let me see. If I let u be x and dv be secant x tangent x dx, then it's going to be pretty clean. We'll just finish it. We'll at least write the line up there. Du would be dx. V would be antiderivative of secant x tangent x is just secant x. Just secant. Just secant, right? So derivative of secant x is secant x tangent x. And then you would have ultraviolet minus integral voodoo and then you need to know what the antiderivative of secant is. But it's on your formula sheet, and you have to have known that it was on your formula sheet. It was wrong page, derivatives, integrals. No, you were there. You were there.
Oh,
Reference page 6. It's formula number 14. Yeah, so this would be x secant x minus natural log absolute value of secant plus tangent x plus c. So this right here is formula 14 on there. So just always remember that you can always find the antiderivative of a single trig function. Like antiderivative of sine, we know that one. Antiderivative of cosine, we know. Antiderivative of tangent, just tangent, it's on there. Antiderivative of just secant, it's on there. Just cosecant, it's on there. Just cotangent, it's on there. Understand? All right.
Is this test on your review?
No. Mm-mm. No, I prefer not to. I stopped posting tests a while back. I just kind of... Why don't you work on that one? I'll give you some time. And substitution u is x squared, which doesn't seem very natural. The derivative of that is 2x dx, right? Which you don't have there. Well, yes, you do. So look, if you rewrite the integral as 2 times x squared times x times cosine x squared dx, that's the same thing, right? Just peeling the x cubed apart. Do you see,
Oh, yes, you do.
you actually have everything. 2x dx, right there, everything. That's du, right? And then this right here is what? U, and then this right here is what? U. So this integral becomes, all that other crap is just du, and then x squared is u, and then cosine x squared is cosine u, and then integration by parts on that.
So that's for W. That was about to give us easy stuff.
Who has the book readily available right here? Let me see. That's insane. Insane in the membrane. Let's see here. Okay, well, you have to start by doing your homework, right? Oh, okay, here we go. So the reason why I was asking for the book, I know we're out of time, because people all freak out about this stuff, and then they get on the test and they take tests. They're like, man, that asshole, he gave us all these problems, and you know, I'm fine in class, and then his test, he makes them so hard and all this stuff. I'm gonna write right now. This is page 316. This is number 29, which is an odd problem in this book. It is integral, and then it has numbers here, which I told you to ignore, right? Theta cubed cosine theta squared d theta. That's this problem right here, using thetas instead of x's. And in the problem here, they didn't give you the 2, so you had to account for that when you worked through it. The moral of the story is that this problem is not something that I'm going to pull out to make the hardest problem possible. If you do your homework, if you do the things that are asked, then you will have experienced this pleasure before you get to the test. If the first time you ever experience this problem is on the test, you probably are not going to get it. Right? So practice. Do your homework. I'm not going to try and pull out the hardest thing I can find, but I will ask you problems that I've asked you to look at. All right? Yes. What is the homework? Yeah, what's the homework for that section? Is it on here? No, you need to go up through 36. Yeah, I think you should try and do 1 through 36.
I think that's what it was.
Yeah, I think it's on the end of the notes. No, oh, here we go. Okay, 1 through 32. See, so look, there it is. You see, I gave that same assignment to my class last semester. Number 29 is in that assignment, right? Number 29 is in there. That's the problem I gave them. The only thing I did was change it from theta to x, and I gave them the 2 so that it worked even better here. Yeah. Okay, go.
You just scale it to the other side, though. Like on this one, you
Yeah,
scale the other
yeah. This one you just have 1/2, but you would have to scale out. I didn't do roll.